presenter has presented at ShmooCon before, so we want to give a warm welcome back to Mark, who will be talking on Hi, My Name is Keyboard. So please give a warm ShmooCon welcome to Mark.
Well, I'm excited to be here and excited to share my new research, and I appreciate y'all coming to survive this after-lunch session with me. This talk is about a number of Bluetooth vulnerabilities I discovered in the last 6 months, some of which have been fixed in the last month or so. I am going to be talking about methods to extract the Bluetooth link key from Apple Magic Keyboard products over the Lightning port or Bluetooth from the keyboard, as well as extracting the link key from the Mac that's paired with the keyboard over the USB port. And then I'll be looking at force pairing and keystroke injection vulnerabilities affecting macOS, iOS, Android, Linux, and Windows. And a little bit about myself. I work as a reverse engineer at SkySafe, where I had the pleasure of reverse engineering drones and their communication systems. I also have a history with wireless keystroke injection bugs. Back in 2016, I did a project called Mousejack. This was my first security research project, and it was a branded vulnerability that was primarily known for injecting keystrokes into Logitech mouse dongles. But it also covered another 20 or so vendors, and it was 17 bugs in total. And all of those were non-Bluetooth. So with that work, I was looking at strictly custom protocols and devices with USB dongles. And I've also had kind of a healthy side project appetite for DARPA challenges. And so I competed in the DARPA Shredder Challenge and Spectrum Challenge in 2012 and 13 and 14, solo as Team Wasabi. And then in 2018 and 19, I collaborated with my good friend Matt Knight, and we competed as How Make Radio in the Spectrum Collaboration Challenge. And I also have this feature where if a device has a radio, I have to hack it. I can't own something with a radio and not know how it works and how it's broken. So these are all the vendors where I've disclosed wirelessly exploitable vulnerabilities. This is primarily between 2016 and 2020, and then a few vendors that were added on with this current research. And it's been a few years since I've done any big research project, and I've been getting kind of the feeling that I need to get back out here and do more of this. And so I was at the Hardware I/O conference in Santa Clara last year, and that was the first multiple-day conference that I had attended since COVID. It was actually the first conference training I had attended, which was a lot of fun. And I had a great time there just hanging out at the lobby, nerding out with friends, new and old. And I realized that I really need more hacker conferences in my life. And so for me, that means breaking things and telling people about it. And so I decided that I wanted to do some kind of a stunt hacking project or some kind of a vulnerability research project. And what made sense to me at the time was looking at gaming keyboards. And this ended up transitioning over to different devices. But my initial thought was that with the Mousejack work, that was all proprietary protocols, and it had been 8 years. And so I figured, in that 8 years, maybe the public shaming that I gave those vendors would have caused them to improve their security standards or their security posture. And I also noticed that this current generation of gaming keyboards has adjustable LEDs, and I really like projects with blinky lights. And so I figured I would buy some of these flagship gaming keyboards from the big peripheral vendors and see if they were any better than the Mousejack era. And unfortunately, they weren't. So there were the first 3 I looked at. I'm not going to mention them by name because they were using unencrypted RF physical layers, and I haven't actually disclosed anything to the gaming keyboard vendors. But normally if I do research like this where I start a project and then squirrel off onto something else, I'll just leave the original work on the floor and not tell anyone. And so I want to hopefully incentivize somebody to take a look at some of these gaming keyboards because they are, I think, pretty hilarious and would make for a fun talk. So the one keyboard I will discuss here with the gaming keyboards is this Alienware AW920K. This was the one that at least made an attempt at doing security. So this was $280 when I first purchased it right when it came out. It uses Nordic NRF52 SoCs. I took a look at first at the RF physical layer going over the air, and I noticed it was encrypted. So it wasn't just plain text HID reports over the air like the other keyboards. Unfortunately, when this keyboard first came out, there were no firmware updates, so there were no Windows tools to reverse engineer and figure out what their DFU protocol looked like. And so I decided to take a look at the USB interface on the dongle. And I found that historically, when I've looked at USB devices, they'll often have some kind of a firmware update mechanism that goes over USB or USB HID. And so I made a little USB control transfer fuzzer which would attempt to write random HID reports on the dongle, and then do bit flips on the commands, 1 or 2 bit flips on the commands that would be known to write to the dongle. And so I pointed this fuzzer at the dongle and ran it for 30 seconds or a minute, and the dongle stopped responding. So I unplugged it, plugged it back into the computer, and it did not enumerate. Now, at this point, I was feeling kind of excited because it looked like there was going to be some fun bug here if I was able to brick this dongle after 30 seconds. When I initially looked at the dongle, it had SWD enabled. They had used the anti-debugger protection, so you couldn't dump the flash memory. But after it was bricked, I decided to look again, and I found that SWD was then enabled, so you could dump the flash memory. So I took a look at the flash memory, and what happened was my fuzzer had somehow erased 2 pages of flash memory from the bootloader. So this meant I could no longer use it, and it was an interesting bug to explore, but I wasn't able to continue any dynamic analysis of the keyboard. So I contacted Dell and tried to buy another dongle. They didn't have the ability to sell me one. They had no way to pair the dongle with my keyboard at that time. And so at this point, I decided that these gaming keyboards were just not going to be very fun, and decided to transition over to Bluetooth. But when I was preparing for this talk, I decided to take another quick look at this keyboard, and I found that Dell had actually published firmware updates for both the keyboard and the USB dongle. And these are Windows executables, which you can download from Dell. And the updates are encrypted, but they're encrypted using an AES key that is derived entirely from the size of each individual firmware image. So there's a script here on a GitHub gist, and I'll tweet this out at the end of the talk. And this is a script that you can use to decrypt and extract those firmware images for this Alienware dongle and keyboard. And my hope is that somebody picks up this project and reports some of these bugs and does a good talk on this, because I think these gaming keyboards, they weren't what I wanted at this time, but I think they're going to make for a fun project and talk for somebody. And so when I did the mousetrack work, that was all custom protocols and nothing with Bluetooth, and also nothing with Apple. And over the last 8 years, these 2 brands, Bluetooth and Apple, have become sort of kind of my white whale. They've been brands that I've been intimidated by, that I've been scared of. And when I was presenting the mousetrack work, I was often asked, what do I recommend people use? And I would always recommend a Bluetooth keyboard, because my thought was that they use all this fancy encryption, therefore it's better than these unencrypted protocols I was looking at. And I also had the same sort of thoughts about Apple. People would ask me, is my Apple keyboard secure? Is my Apple mouse secure? And I would say, probably yes, because it uses Bluetooth. And I fell victim to Apple's marketing and all this common wisdom that says these ubiquitous protocols like Bluetooth that everyone uses are inherently secure, because if they weren't, somebody would have found the bugs. And same with Apple. Everybody looks at Apple products, everybody speaks highly of them. I didn't have any Apple experience before this research, but I just kind of assumed that Apple was going to be beyond my ability. But now, 8 years have passed since Mousetrack, and I've leveled up my skill set, and I've also gotten a lot more comfortable with failure. And so I decided it was finally time to look at Apple and look at Bluetooth and see what I could find. And so I started by buying this Apple Magic Keyboard, the A2450. This is their cheapest keyboard, $100 I think it is. And it can function as either a USB keyboard or a Bluetooth keyboard. If you connect it to the Mac with a USB to Lightning cable, it talks over USB. When it's unplugged, it talks over Bluetooth. And before we get into some of these fun Apple bugs, I want to spend a few minutes and talk about Bluetooth and HID. Bluetooth is an enormous protocol. The specification is thousands of pages long, and it's thousands of pages of English text that describe complicated state machines, which in my mind feels like something that could be full of bugs, but also kind of daunting because of how much content there is. Same with HID. The HID specification is not quite as daunting as Bluetooth. HID is used over USB and Bluetooth. And I found that I had a lot of ideas about Bluetooth, but I was only partially informed. And so one misconception I had is conflating Bluetooth Classic with Bluetooth Low Energy. So Bluetooth Classic, this is the original Bluetooth protocol. This is what was around from the beginning with Bluetooth, and then Bluetooth Low Energy was introduced in Bluetooth 4.0. And BLE was actually originally called Wybri. It was a protocol developed by Nokia, and so it has a Bluetooth name, but that's really because it's part of the Bluetooth brand, and it's not compatible over the air. It is a completely distinct physical layer protocol. And I also realized that I thought I knew how the application layer worked with Bluetooth, but I was completely clueless. And so, for instance, I didn't realize that there's a distinction between BLE and Bluetooth Classic keyboards. So Bluetooth Classic keyboards use the HID profile, and Bluetooth Low Energy keyboards use something called the HID over gap profile. And so all the Bluetooth bugs I'll be talking about today are specific to Bluetooth Classic keyboards using the Bluetooth HID profile. And so at the lowest level, if you want to connect to a Bluetooth Classic device, you use something called an L2 cap socket. And L2 cap is sort of like TCP, at least conceptually. And to connect to a Bluetooth device, you need to know its address and a port number, and then you can connect, and you can open up a socket and read and write data. Then a Bluetooth profile is this concept of an application layer API that describes a specific use case for Bluetooth. So Bluetooth HID describes a use case for keyboards and mice and gamepads and that sort of thing. You have audio profiles, you have networking profiles, file transfer profiles, and in total, the Bluetooth specification defines approximately 88, by my count, different profiles. Most hosts, so that would be commonly things like phones and computers, support maybe 10 to 20 profiles, and most of these devices support the Bluetooth HID profile. So if you want to identify which profiles a device supports, you do something called service discovery. And so when you put your Bluetooth device into discoverable mode, what that means is you are running an unauthenticated public SDP service on L2 cap port 1. So discovery is always unauthenticated. If your device is trying to search for nearby devices to connect to, it will connect to their service discovery protocol services and enumerate the profiles they support. And then based on that profile enumeration, it will know what services it can connect to. So the HID profile, this is the Bluetooth HID profile, uses two L2 cap ports. It has a control channel on L2 cap 17 and an interrupt channel on L2 cap 19. And if you've worked with USB HID, this is akin to the control and interrupt transfers you can do with USB. The control channel is a high latency channel used for things like configuration and reading and writing settings on the device. And the interrupt channel is a low latency channel, which is used for things like input going to the host, so keystrokes and mouse movement, as well as commands and state change going from the host to the peripheral. And so over these control and interrupt channels, the devices send things called HID reports. And a HID report is just a simple data structure, sort of like a TLV type structure. You have input reports, which are going from the peripheral to the host, output from the host to the peripheral. Then have feature reports, which are used for the host to read and write persistent settings on the device. And feature reports are sort of like a key value store that allows the host to write persistent settings to the device. And so assuming that you are paired with a host that supports Bluetooth HID, you can generally connect to that host and inject keystrokes by connecting to L2 cap ports 17 and 19. So this assumes, again, that you're already paired, but then you just connect to those two ports, and then you can send HID reports, HID input reports with keystroke data to the host. And as this requires pairing, I want to touch on some pairing concepts which I had been confusing prior to this work. So what I have always called pairing is really pairing and bonding. Pairing is this temporary process of establishing a link key, which is more or less a session key between the host and peripheral, and it's used to encrypt the traffic between those two devices. And then bonding is a process of saving that session key, that link key, to each device. So pairing is a temporary process, and bonding is the process of doing that permanently. And so when you go to through a UI on your device and you select a Bluetooth peripheral to pair to, and you pair with it, what you're really doing is pairing and bonding. And then out-of-band pairing is a process of going through pairing and bonding over a non-Bluetooth channel. And so commonly that's NFC, where you might tap two devices together and then you're paired. It could also be over USB, as a Magic Keyboard out-of-band pairing works. And you could also have devices which have a link key which is programmed into non-volatile memory at the factory, for instance. There is no specific constraints on how out-of-band pairing is performed. And while devices are performing pairing over Bluetooth, the devices advertise what they call a pairing capability. And this states what type of authentication the device supports. And so that might be numeric comparison, where you have the host and the peripheral each displaying a number on their screen, and then the user has to say these numbers are the same. You have passkey entry, where you have a number displayed on one device. That number has to be entered by the user on another device to pair. But you also have these unauthenticated pairing mechanisms that are ostensibly for things like Bluetooth mice or other devices that don't have this ability to display or enter a number. And no input, no output pairing is what we're exploiting in a lot of these vulnerabilities today. And no input, no output states that I have no ability to give you any numbers, and I can't receive any numbers from you, ostensibly. So with that little bit of history on Bluetooth and HID, let's take a look at how we can actually hack these Apple keyboards. And so the first keyboard I got, I wanted to do some hardware analysis, and I did sort of an unintentional destructive disassembly. I was pulling the keyboard apart, and I didn't really understand how much adhesive Apple likes to use in their products, and I ripped it too hard and snapped the PCB. And so the second Magic Keyboard I bought, I decided to take a little bit of a lighter touch approach. And I didn't know enough about how Bluetooth HID worked at the time in order to attack it over the air, and so I started over USB. And I took that same USB control transfer fuzzer that I had pointed at the Alienware dongle, and I pointed it at the Magic Keyboard. And I thought for sure maybe there would be a bootloader command I could find or something, but after 30 seconds, the Magic Keyboard also bricked and stopped responding over USB. So I unplugged it, plugged it back into my Linux laptop, and I saw that the device descriptor could not be read from the keyboard. And so the device descriptor is a USB data structure which tells the host what type of device is plugged in. And this is one of the first parts of doing connection establishment over USB. And so if the device descriptor can't be read, that means something has gone horribly wrong on the keyboard. And so I dug into this a little bit more and tried to understand exactly what was going on. And I was able to characterize that the fuzzer had written a null device descriptor to the Magic Keyboard. And it turns out that the device descriptor on the Magic Keyboard is something that can be written over USB. And this was new to me. I hadn't observed these writable descriptors before. Similarly, there are a bunch of writable HID feature reports. These are the reports that are used for configuring settings on the device. And so over USB, an unauthenticated host can change the product name, serial number, can write the device descriptor as well as some other descriptors, and can also write the Bluetooth address of the keyboard. And so at this point, it looked like this might be something that could be used as part of the normal operation of the device. And so I started wondering, how does Apple's pairing utilize these write primitives, if at all? And so the way you pair your Magic Keyboard with your Mac, you plug it in with a USB to Lightning cable. When you do that, it's magically paired. You unplug it, and it magically connects over Bluetooth to the host. And so I decided to check if any USB descriptors or HID reports were written during this pairing process. So I started by dumping all of the HID reports and USB descriptors from the Magic Keyboard to a text file. I then plugged it into the Mac, unplugged it, and dumped the reports and descriptors again. And then I just diffed those text files to see what had changed. And there were a lot of things that were changed by a bit flip here or there, or some counters, or some minor state information. And it was mostly innocuous, except for this HID feature report 0x35. And this started out as mostly 0 bytes before pairing with the Mac. After pairing over USB, it is mostly non-0 bytes. And what we can see here, it looks kind of like a high entropy string, which is usually fun when we're talking about pairing or encryption. And so I noticed that 6 bytes toward the front of this matched the Bluetooth address of the Mac that I had plugged the keyboard into. And that leaves 16 bytes of high entropy data at the end. And at this point, I thought this was going to be something good, but I also didn't know enough about how Bluetooth pairing or encryption worked to really know what I was looking at. And so this felt good, but I needed to learn a little bit more. And so at this point, I realized I needed to get a little bit more comfortable with this Mac that I had bought. And I spent a couple weeks asking some very basic questions of my friends of, how do I do these basic things on an Apple computer? It was humbling and uncomfortable at first, but after I got my bearings, I discovered that Apple loves verbose logging. And so everything I've looked at so far in the Apple ecosystem has extremely verbose logging that tells you exactly what the software or device is doing. And so the Bluetooth daemon on macOS has these great logs which tell us that when we plug the keyboard in, the Bluetooth daemon generates a link key and then sends it to the keyboard. And so based just on these logs, I've inferred that that 16-byte high-entropy string at the end of that HID report is potentially the Bluetooth link key. And this turned out to be correct, and so we have this HID report 0x35 is what we refer to as the out-of-band pairing data. And so this is a link key and a Bluetooth address that is sent to the keyboard, and then the keyboard uses this to know which computer to connect to when the cable is unplugged. And so I was wondering, is this link key something that is generated and set once? If I read the link key out of the keyboard, do I only get to use that until the keyboard is next plugged in, or does it persist? And so I ran through this pairing process a few more times, and I observed that the logs changed on the second and further pairing attempts. And what happens is when you plug the keyboard in a second time, the Mac will recognize that keyboard and send the same link key over USB. So this means if we can read the link key for the magic keyboard, we can then use that for the duration of the time that that keyboard is used with that Mac. And so this gives us our first vulnerability, which is the ability to read the link key for the magic keyboard over the Lightning port. So the way this works, you plug the Mac into the magic keyboard, unplug the magic keyboard, then as long as that keyboard remains powered on, an attacker can come by and plug into the Lightning port and get the link key. Then once you have that link key, you can use that to impersonate the keyboard and inject keystrokes into the Mac, or as one half of a machine in the middle attack. And so at this point, I was starting to get a little bit more comfortable and familiar with Bluetooth, and I started to read some of the Bluetooth HID specification. And what I noticed is that there's a ton of backward compatibility logic in there. And so Bluetooth, I think, as an organization, strives to be able to connect as many different types of devices over the same Bluetooth link. But in order to do that, you're beholden to the lowest common denominator of the security posture of whatever devices you're using. And so if you want to support all the devices, that means you have to support devices that support this no input, no output authentication-free pairing mechanism. With this criteria here, this states that if you are trying to support, from a device standpoint, trying to support an older Bluetooth host, when you become discoverable as a device, you have to run an unauthenticated Bluetooth HID service on your, in this case, keyboard. And so this means that in the case of the magic keyboard, when you power it on, it becomes discoverable, and it also runs an unauthenticated HID service on the keyboard. And so at first, this sounds like something we could use to potentially read the link key off the keyboard over Bluetooth. But the problem is this only becomes discoverable when the Bluetooth radio is powered on. And so when we switch on the keyboard, the link key is no longer in memory in that HID report. And so then I started looking at this handoff between USB to Bluetooth. So this transition when you unplug the keyboard, where it changes from going over USB HID to over Bluetooth HID. And the way this works, send the link key over USB, and then as soon as the unplug event happens, the keyboard connects to the Mac, and the Mac tries to connect to the keyboard. And it turns out there's actually a timing trigger that we can use in this flow to be able to catch the magic keyboard when the Bluetooth radio comes online after being unplugged from USB. And in that moment, the link key is in memory in that HID report. And also, because the Bluetooth radio has just come online, it is discoverable, and it is running the unauthenticated HID services. So what we can do is an attacker can spoof the address of the magic keyboard and connect to the Mac while the magic keyboard is plugged in over USB. And then as soon as the keyboard is unplugged, the Mac will try to connect to the magic keyboard. But because the attacker spoofing the keyboard is connected to the SDP service on the Mac thinks that it already is connected to the magic keyboard, and it connects to the SDP service on the attacker's machine. And this gives us a very precise timing trigger for when that unplug event happens. And so using this SDP timing trigger, we can actually read the link key from the magic keyboard over unauthenticated Bluetooth. And so as soon as the keyboard is unplugged, we get that SDP connection. We then connect to the unauthenticated HID service on the magic keyboard and are able to read the link key over unauthenticated Bluetooth. And this is pretty bad, because this means if an attacker can observe a keyboard getting unplugged from the Mac, they can read the link key and then later use that to intercept the link or inject keystrokes into the Mac. And so at this point, I was feeling more confident about Apple, more confident about Bluetooth, and I started to look more into the Bluetooth daemon on the Mac. And I wanted to know, how does this Bluetooth daemon authenticate the keyboard? Because the first time we plug it in, it generates a link key, sends it to the keyboard. Next time we plug it in, the Mac recognizes that keyboard. And so I started looking through the logs to try to figure out how this keyboard is recognized. And I noticed right away that the Bluetooth daemon identifies itself as the Bluetooth Super Server Robot Destroyer. And in my experience, when you see kind of overconfident feeling comments like this or logs like this, it points to engineers who haven't learned all of the necessary security lessons to do things right. And so I wanted to know, how does this robot destroyer identify the keyboard? And it turns out by its Bluetooth address and serial number. And if you remember, these are two of the fields that we can actually write over USB on a keyboard. And so this gives us an attack vector to read the link key from the screen-locked Mac or screen-unlocked Mac. We have our donor keyboard, which we configure to look like the target keyboard by writing the target keyboard's Bluetooth address and serial number to the appropriate HID reports and USB descriptors. We plug our donor keyboard into the target Mac and then unplug it. And then we read the link key of the target keyboard off of our donor keyboard. So this attack requires that you know the serial number and Bluetooth address of the target keyboard and have access to the Mac. but allows you to get that link key out of the Mac itself without physical access to the keyboard. And so we have 3 mechanisms now to extract the link key from the keyboard. We can do it over Lightning from the keyboard itself, over unauthenticated Bluetooth from the keyboard, and then for the Mac over USB. And just as the Mac can write out-of-band pairing data to the keyboard, so can an attacker. So when somebody powers on their Magic Keyboard, an attacker can connect to that unauthenticated HID service, write new out-of-band pairing data, and cause that keyboard to connect to a machine of the attacker that the attacker has specifically configured. And so you can use this to then redirect somebody's Magic Keyboard to your computer and intercept what they're typing. And you can also do this over USB, or over Lightning port rather. So if you have physical access to a Magic Keyboard, you can plug into it, write a new set of out-of-band pairing data to it, and have that keyboard connect to the device that you control. And so at this point, it really started to feel like we were close to a machine-in-the-middle attack, because there was a mechanism where if we have the Bluetooth link key, you can spoof the keyboard and connect to the Mac. And then there's this unauthenticated HID service on the keyboard, which gives us the other half of the machine-in-the-middle link. And so I wanted to flesh this out, and I didn't really know how to do it. So I started by just experimenting with having a Python script that would connect to L2CAP ports 1 for SDP and then 17 and 19 for HID on both the keyboard or the Mac while spoofing one or both addresses. I would try this in different sequence orders and different host configurations for my script. And eventually I discovered that you don't actually need the link key to connect to the Mac. And so I ditched the MITM effort, and this is something that I think somebody else will have some fun fleshing out a good timing attack there. And so there's now this forced pairing mechanism where if we connect as an attacker to the Mac at the exact time the Mac is trying to connect to its Magic Keyboard, the Mac will actually let us pair without authentication, and it will ignore the fact that the Mac already has established a link key with the keyboard, and it will drop that on the floor, let us pair, we get a new link key, and then we can inject keystrokes into the Mac. This is a fun attack vector, but it's difficult in that it requires a precise timing mechanism. And so we can't do this arbitrarily. We can only do this when the user unplugs the keyboard. So we can use that SDP timing trigger, and we can detect exactly when the keyboard was unplugged from the Mac. We can then connect the Mac over HID services on L2CAP 17 and 19, specify no input, no output pairing, and then the Mac will pair with us without any user confirmation or anything in the UI at all. So this is a screen recording of this attack on a Mac OS machine. At the loop of the GIF is when the keyboard is unplugged, and then it takes a couple seconds later, and the attacker is then force paired and is able to inject keystrokes to, in this case, perform a Google search in a web browser. And so what is happening here? Why does this work? Again, this is because of this no input, no output pairing mechanism, but this also requires certain criteria on the host. So we can do this type of attack when the host supports no input, no output pairing. The host also has to not show any user confirmation when using this pairing mechanism. And amazingly, most hosts do not show or do not request user confirmation when using no input, no output. And then the host also has to allow pairing to be initiated by the peripheral. So this means instead of pairing by selecting a device from the list on the host, the peripheral itself has to be able to initiate pairing. And this is also very common, it turns out. And so, at this point, I was feeling confident enough with Mac OS that I felt like I could branch out and look at some other platforms. And I didn't know, what the delta was between the Bluetooth behavior on Mac and Bluetooth behavior on iOS. And so one thing right away that stood out to me is that on iOS, you don't have the USB out-of-band pairing, because you don't plug your iPhone into a Magic Keyboard to pair, you pair over Bluetooth. But it turns out you don't actually need that out-of-band pairing mechanism for the trigger. The service discovery protocol trigger that I identified, I thought at first it was going to be specific to that unplug event, but it's actually specific to the host trying to connect to the peripheral. So the same SDP trigger that works when we unplug the Magic Keyboard from the Mac also works when the iPhone is trying to connect to a Magic Keyboard that it is paired with. And so this means we can do the same attack on an iPhone paired with a Magic Keyboard or iPad at the moment that the user is trying to reconnect to a keyboard that they've already paired. This affects iOS 16 and 17 per my testing. I haven't tested earlier iOS because I'm only using this new to me iPhone that I have for a dev phone, and I don't have any older devices to test on. So this is a video of a screen grab from this attack on an iPhone. And when I hit play here, what we'll see is the phone is at the Bluetooth settings page. The user clicks on their already paired keyboard in the list, and instead of connecting to that keyboard, the phone will pair with the attacker's machine, who then injects a keystroke payload. And we see the pin number flash by there. And so what happens is there's a pin displayed, but that's just ignored, and the user is able to pair anyway. I'll play that one more time here. So we see that pin flash by, and that's, again, just ignored. So after seeing this on macOS and iOS, I wanted to know, does this also affect Android? And Android is an ecosystem that I have a lot more familiarity with. I've been an Android user for a long time, and so I also had a long history of Android devices to test against. So I reproduced the iOS attack exactly on Android, or I thought exactly. And sure enough, it worked. I was able to pair and inject keystrokes into the Android device. But what I realized after the fact is that I had screwed up the POC, and I had been spoofing an address of a keyboard that was not paired with an Android phone. So I paired keyboard A with the phone, and then was spoofing keyboard B, and the attack worked anyway. And after investigating this, it turns out that on Android, there is no spoofing requirement. The user does not have to have a keyboard paired with their phone already, and as long as Bluetooth is enabled on the Android device, at any time that the phone is on and Bluetooth is on, the attacker can then force pair a emulated keyboard with the Android device and inject keystrokes, including at the lock screen. And because I have this collection of Android devices, I was able to go back and test this all the way back to Android 4.2.2. So Android approximately 4.2.2 through Android 14 is vulnerable. Google fixed this in the December 5th security patch level from last month. This hasn't rolled out on all of the devices. This can be applied to Android 11 to 14, but that requires that your device manufacturer or carrier supports this and rolls it out. So the device that I reported this to Google on was the Pixel 4a 5G, and that hit its last security update in November of last year. And so the device I reported it on is actually never getting fixed for this bug. And so now that I saw this on Android, I decided to go and check it on Linux. And it turns out that the Linux attack is very, very similar. It had been fixed once before, and we'll get to that in a moment. So on Linux, as long as the host is discoverable and connectable over Bluetooth, the attacker can force pair a keyboard and inject keystrokes without user confirmation. And so this is distinct from Android in that on Android, the device has to only be connectable, but it has to be discoverable and connectable on Linux for the attack. And so this bug was actually fixed in the BlueStack back in 2020. But the 2020 fix was left disabled by default. So all of the Linux distributions rolled this fix in. They announced that they had fixed this bug, but nobody had turned it on except for Chrome OS. All the other distributions had applied the patch but left it disabled. So there is a new patch that has been rolling out in December, which essentially turns on the 2020 fix by default. And so Linux distributions running Blues 5.x are generally vulnerable prior to receiving this patch. So this is a screen grab of the attack on Ubuntu. Here we have the malicious keyboard showing up on the device list. Now without any user action, it is connected and able to inject keystrokes. And similar to Android, it takes 2 or 3 seconds between the attacker launching the attack and the connection being established and being able to inject keystrokes. We'll let this loop one more time. And so because the patch for this in December was just enabling the fix that had been developed in 2020, it's a 2-line patch. And this is one of the 2 lines. And this is my favorite one. And this makes me feel so good as a security practitioner to have something change from defaulting to false to maximize device compatibility to defaulting to true for security. And that just feels good to see. And at this point, this was kind of mid-August of last year, and it was getting to Burning Man time, and so I had 5 or 6 weeks where I was scrambling for that and out of commission on this project. And so I finally got back to the project toward the end of September and found that there's a similar bug in Windows. Now the Windows bug is not 0-click like the other ones. It requires user interaction. The way this attack works, the victim has to have a Bluetooth keyboard paired with their Windows machine, and that keyboard has to be powered off or out of range. The attacker spoofs the address of that keyboard and connects to the Windows machine over Bluetooth on the HID services, specifying the no input, no output pairing capability. When they do this, the user will see a little notification dialog in the bottom right of their screen saying their keyboard wants to pair. If they click on that, they will see a pairing dialog come up on the screen, and they have to interact with the pairing dialog in some way for the attack to work. They can accept the pairing request or reject it or just close the dialog, but as soon as they interact with that dialog, the attacker is able to complete pairing and then inject keystrokes into the Windows machine. And I only tested this on Windows 10, but Microsoft has patched this in Windows 10, 11, and Server 2022, and those patches rolled out on Tuesday. And so now I'm going to do a demo targeting an Android device. This will be targeting a Pixel 7 that is running the November 2023 patch level. And what I'll show you is something I've been experimenting with doing some lock screen fuzzing over Bluetooth HID. And so because these attacks actually on Mac OS and Linux and Android, all three OSs allow you to do the forced pairing at the lock screen. And so I've been curious if it's viable to use this for doing any kind of HID fuzzing for lock screen bypasses. And so I'll show you what this fuzzer looks like here. And it will connect to the Pixel 7 and then inject random key chords. And the key chords are combinations of like Control, Alt, Shift, the Windows key, and then a random HID key code. Okay, so that's mirroring the phone that I have here. And then I will run this script. Okay, so this is attempting to connect to the phone. It is connected and is starting to inject keystrokes. There's a couple seconds lag on the screen mirroring there. And what we're seeing here is just these random key chords being injected into this Android phone at the lock screen. And so this means, if you have your phone in your pocket, somebody could be actively fuzzing your lock screen without your knowledge, which is kind of terrifying in my opinion. And so as part of the disclosure, Bluetooth SIG got looped in, and they had this interesting assessment of the bugs. It was my opinion that this was a protocol level vulnerability, and it's Bluetooth's opinion that this is a vendor problem. And so I think the general perspective that Bluetooth SIG has is that we will give you the gun, we will point it at your foot, and it's your responsibility not to pull the trigger. And unfortunately, their stance is everybody implemented the same bugs, but the reality is that this happens because everybody has been implementing the same specification, which has these bugs baked into it. So I respectfully disagree with the Bluetooth SIG stance on this. And so I disclosed these bugs between August and September of 2023. The bulk of them were in the start of August. The Windows disclosure came at the very end of September. I want to thank Microsoft for getting a patch out in time for ShmooCon, because I just had the feeling that with POC code coming out today that any OSs I had not disclosed in would be quickly found by the community. The Android, Linux, iOS, and macOS patches landed in December. Windows Fix landed on Tuesday. The Magic Keyboard firmware update started rolling out this week. Apple put out their security advisory on Thursday. Those are rolled out automatically, so if you have a Magic Keyboard that is currently paired with a Mac that is online, it will probably have already received the firmware update. If your keyboard has not been connected to a Mac that is online, it is probably still vulnerable. One thing I noticed with the older firmware, prior to this patch, it's possible to do a replay of the DFU where you can write a lower version number to a HID descriptor on the keyboard, and then the Mac will actually replay the current firmware update to it. So if you're interested in exploring that DFU process, I recommend not updating your Magic Keyboard to the latest firmware, which fixed that bug. And I also want to give a big thanks to Mark Essler of Canonical. He was a big help in wrangling the Linux and Blue side of this disclosure. I had never disclosed to an open source project before, and it's kind of a hassle. It was a lot more complicated than I expected. And so big thanks to Mark Essler for helping to wrangle that side of things. And again, a big thanks to all the vendors for getting all these patches out in time for ShmooCon. So the aftermath, I think, is still going to be unknown for a while, but some initial data points. Fixing the Android bug broke fast pair and nearby share on Android. So these are technologies which run on Bluetooth. Nearby share is Google's technology, which is kind of like AirDrop. And then fast pair allows you to discover devices that are close by to you outside of the SDP process, which is faster discovery of nearby devices. Unfortunately, the fix broke that because those services were running over unauthenticated Bluetooth, and they were doing encrypted communications, but over this unencrypted, unauthenticated channel. fixing the Linux bug, broke support for game controllers in Linux, so PS3 controller and a bunch of others are no longer able to be paired with Linux. I have headphones, which I can no longer use with Linux. And I think this is the tip of the iceberg. I think once a full impact is known, I think it'll probably be a while because it will take the community actually fleshing these out and identifying all these additional affected systems beyond what I've seen myself. So, I think it's easy to blame the vendors or blame the Bluetooth SIG, but I think there's shared responsibility here. I think the vendors definitely dropped the ball by missing these bugs. Some of them have been around for more than a decade. I think we, though, as the hacker community, dropped the ball by not finding these. And I think it's kind of embarrassing that we let these bugs that are really easy to exploit and easy to find once you look for them, we let these sit here for over a decade. And so I think, everybody can improve in this process. But the nice thing is that we're all humans. Humans make mistakes, and that's OK. That's just part of being human. And I view this as a positive thing, because if these bugs have been hiding in plain sight for so long, I just am excited to find out what other bugs fit the same bill. And so I encourage you to take some technology, some device, some service that you rely on a daily basis that you assume is secure, because everyone thinks it's secure, and start poking at it and get familiar with it and find out, is it actually secure, or are you just assuming it is because everybody else assumes it is? And with that, I have published the POC code for all of these vulnerabilities on GitHub, and I look forward to feedback from the community as we discover the full set of affected devices. And with that, we have time for a few questions.
At one point, you were talking about how you could potentially do a machine-in-the-middle attack on the keyboard, but then I think you said you transitioned away from that tech. I didn't understand the reason why you discontinued that line of breach.
Yeah, so the reason and just to repeat the question was I mentioned I had done some work on machine-in-the-middle attack and then transitioned away from that. The reason I had transitioned away was because I was most interested in injecting keystrokes into the Mac. There is a viable machine-in-the-middle attack scenario which I have validated, but it's not a clean scenario. So the way this works, when you connect to the to the Magic Keyboard's unauthenticated HID service at that unplug event, sometimes it's possible to connect immediately to the Magic Keyboard and get the link key, but sometimes there is a timeout of 25 seconds somewhere in firmware that you have to wait for. And so it's possible to do the MITM attack in that scenario, but it doesn't make for a very viable scenario because you have 25 seconds where the user would observe that they can't use their keyboard. And at the end of that 25 seconds, you can use the link key to connect to the Mac and maintain your connection with the keyboard. But I think it's not the immediate unplug MITM attack that I was looking for. That said, I think it's still viable, but I just haven't fleshed out what specific sequence of events needs to happen to do that in one immediate action.
All right, then the one thing I'd recommend checking out is in the last couple of years, there have been at least 3 or 4 academic papers on active machine-in-the-middle attacks with existing connected devices. So since you already have everything set up and the system all understood, I'd check out those academic papers and see if you can just take an active existing Bluetooth connection between a Mac and keyboard and just get in the middle with it with one of their techniques.
Yeah, I appreciate the recommendation. I look forward to seeing what the current research is on that.
Hey there. It was really neat to see the fuzzing of the lock screen and the tools you're building there. Where do you see that part of your research going next?
TBD. I think I'm going to continue doing some fuzzing on different platforms to see if there are any lock screen bypasses, for instance. But I don't have a good sense for what the actual attack vector will be, what sequence of events might be likely to trigger a lock screen bypass. So at this moment, it's just kind of exploratory fuzzing.
Great, thanks.
OK, I think that's it. Thank you all so much.
Real quick question. Were you rightfully compensated for this research?
So I've received a $1,000 bounty from Microsoft and a $15,000 bounty from Google, and waiting on Apple's decisions.
All right, that's good to hear. Probably a little low, though.
Yeah. All right, thank you.